Okay, hi, I'm Justin. I'm this year's Pocket Racers lead, and I'll sort of briefly go over what the project is and a summary of this year, and then we'll move on to like some of the stuff we did this year more specifically. So basically, Pocket Racers is a project that was conceived about like making a 3D printed car that's driven by computer vision, and it'll be able to autonomously navigate a track. So in order to sort of meet this goal, we have like a curriculum. We teach things like Raspberry Pi. Our car is like the brain of it is the Raspberry Pi. And then we teach things like basic machine learning, which is sort of roughly up to like convolutional neural networks, including stuff like backpropagation and like optimizers and stuff like that. We also teach like more computer vision specific stuff, like localization in images and contours. Specifically, this is just referring to stuff found in like a Python package OpenCV. So we are primarily like, a lot of our curriculum is like computer science based and nested in Python. So what do the Pocket Racers students do over the year? I mean, we'll get into it in a second, but basically over the course of the year, the teams assemble their cars and then they learn how to set up like some of the hardware on their cars, like the Raspberry Pi and the motor. And then they do like an assortment of machine learning labs to sort of familiarize themselves with the concepts and stuff like that. And they also do a bunch of computer vision stuff that's central around the car, like detecting signs, detecting dice, dots, which you guys will learn a little bit more about in a second. In terms of who our like pool of candidates were, or sorry, our members were this year, we had 36 students, all of which were pretty much varying levels of experience, though we tended to prefer the bigger or the beginner levels. And we took 36 students, like I said, and we ended up subdividing this into 12 teams. So now you'll hear from two of our students, and also they happen to be next year's leads.
Hi. Yeah, so one of the first things we did in our goal of developing a self-driving computer vision run car was being able to detect things using computer vision. So we did this in a lab involving dice dot detection, and our job was to get the information from the camera from the Raspberry Pi and being able to isolate and count how many dots are on the dice. And we do this by cutting out like extra background information, because for a computer, an image is just a bunch of numbers and it can't really process what it's seeing. So in order to do that, we have to cut out a lot of background information while making sure you don't cut out anything that's important in like counting what's on the dice. So some of the steps that we took in order to do this process was like downscaling the image, just so there's less information, and then blurring the image, and then thresholding, which is like trying to determine like where the edges and important features are without getting rid of them, and getting rid of all the extra noise that aren't those features. And then erosion and dilation. The goal of this was, thresholding can only get rid of so much noise. Erosion and dilation will get rid of some extra noise in the blobs that we see. And then we did blob detection. So once we were able to isolate the dice circles that we wanted to count, we used blob detection to detect them and count them. And then outside of the dice, we also practice using colored dice, because typically we just put things in grayscale. But if you want to do this for colored dice, we learned how to use like HSV filters in order to do so. And then also, since the camera picks up so much background, we also learned how to get rid of some of that background. And yeah, we also learned how to deal with shadows and how different lighting affects things, as well as different backgrounds. And yeah, we were able to detect things using our Raspberry Pi camera.
So once we learned how to use these computer vision techniques on the dice, we were able to sort of apply them to something that would be a little bit more interesting from moving a car's perspective. So we have a bunch of signs that we created, like a stop sign, straight sign, and then we just rotate that to make it right and left. And our goal is to detect that so that we can tell the car, let's move to this direction or this direction, or let's stop. And so we combined those techniques that we just learned about with some other techniques, like finding a midpoint, so that we can also find like the center of mass, so to speak. It's more of like the center of volume. if you like to think about it that way, to figure out if it's right or left. And so we were able to use these heuristic methods of computer vision to detect a sign and actually move the car in some way that we wanted to move it. So yeah, that was cool. And this is a little demonstration of it detecting what the direction is and then outputting a PWM signal to the motor, to the servo, so it knows which direction to go. So that's pretty cool. And
Unfortunately, we do have limited budget, and this also is IEEE's newest project, so we still are sort of developing our project as we're going. So originally the intent was stated for this project to be essentially machine learning driving a car around a track, but it proved to be a little bit difficult for a bunch of mechanical, electrical, and also machine learning related problems. So we had to scale back a little bit this year, although you'll hear about these two's next year's plans, which will be very interesting. Essentially for this year, we're going to do something, or we have been doing something a little bit different, and hopefully we'll have some results by the end of the quarter. And essentially what we're doing is, instead of having to collect a data set to train on, we'll generate a data set instead using essentially image homography. And then we can essentially simulate what it'd be like to essentially have a sign in various positions from the camera's perspective, and essentially be able to train a neural network to be able to classify these. This way, it's more robust than those heuristic methods that we employed earlier in the year. It's a little more general, and it should overall be able to have a better performance in that regard. But that's essentially it for this year, though these two have some pretty big plans for next year that they would like to talk about.
yeah, so Pocket Racers is a pretty new project. So we're searching for ways to optimize the project, and we're doing a lot of iterative changes to the curriculum. So this year we're going to try something different where we focus on the machine learning itself, and we just have a platform that we don't have to develop ourselves. So we're going to focus more on the software. And for this, we're probably going to go with the Amazon Deep Racer. We're doing a discovery phase right now, so it's not set in stone yet, but it would be really interesting because we can make use of the LiDAR and the camera. Amazon has great tools for doing reinforcement learning on the Amazon Deep Racer. So we're really excited to explore this as a potential capstone project or advanced course for next year.
Yeah. So along with this one, we also planned on, so this research on the Deep Racer would be more complicated and would probably require some background knowledge. So we hope to keep Pocket Racers also being beginner friendly. So we were gonna keep this as a track, as well as having another track where we use the current stuff that we used this year, like the 3D printed car and the Raspberry Pi camera. And we're gonna keep trying to work on that, as well as working on this for the more advanced people. So that way we can have, for beginners and as for more advanced people, and trying to further the project.
Yeah, we're really excited.
Thank you.
I'm sorry, quick question. How does blob detection work? What's the math behind that?
Great question. There's some algorithms that you can learn about, that we learned about specifically in our computer vision class. I believe the one that's used is probably SIFT, right?
Yeah.
Yeah, so there's this algorithm called SIFT that does this sort of Gaussian filter on the entire image, and it's really complicated, but the essential idea is that you try to find where this filter has a peak, and then wherever that peak is, there's a blob that was detected. And so that's on a very 10,000 foot level.
Okay, and it assumes blob is circular or
Yes,
not?
yes, exactly. Yep. You
Okay.
have to assume that.
Although, not necessarily, depending on how you adjust some certain parameters and stuff like that.
For sure.
You
Yeah.
can use you can check the blobs for their circularity or convexity to determine the actual shape of them.
Okay.
Yeah.
Right. Oh, I'm sorry, but you mentioned you're kind of use some neural networks to identify the different angles of the arrows. And you're comparing it to what you did before. You said you used some heuristics in the past. Could you explain the heuristics you used?
Well, the heuristic methods are basically what we just talked about with the erosion, dilation, center of mass, and then finding the midpoint. Those are all heuristic methods to kind of say, we think this is the sign that we are finding, instead of letting the neural network figure it out for us. Yeah.
Thank you.
Thank you.